Okay, so the next question that we have is basically it's a good question and it tests your understanding of polynomials and that sort of thing. So it says that let a1, a2, a3 all the way up to a of n be fixed real numbers and define a function. Define a function f of x is equal to x minus a1 times x minus a2 times all the way up to x minus a of n, which is of course a polynomial. And what you want to do over here, let me delete all of this. So basically this is the question. Now basically now what you want to do is, what is the limit of f of x as x tends to a1? So basically we said that, so now you know that these are the zeros of the polynomial, meaning that, for example, let's say that, let's make up some polynomial. For example, let's say that 2 is the zero of a polynomial, negative 3 is the zero of a polynomial, and positive 5 is the zero of a polynomial, these three numbers. So then you will be able to write your polynomial as f of x is equal to x minus 2 times x minus negative 3 times x minus 5, which is the same thing as x minus 2 times x plus 3 times x minus 5. That is your f of x. And of course you can rewrite this polynomial as, for example, if you multiply these two together, you'll get x squared plus 3x minus 2x minus 6 times x minus 5, which is equal to x squared 3x minus 2x plus x minus 6 times x minus 5, which is equal to x cubed minus 5x squared, x cubed minus 5x squared plus x squared minus 5x minus 6x plus 30, which is equal to x cubed minus 4x squared negative 11x plus 30. So this is your polynomial. This would be your polynomial. So then you can write your f, you can say that your f of x is x cubed minus 4x squared minus 11x plus 30, which means that when you factorize this polynomial, you will get these factors as x minus 2, x plus 3, and x minus 5, which means that the zeros of this polynomial are these three numbers. And of course, since you have three zeros, it's a third degree polynomial. So far we have no problem. And of course you know that your polynomial at your zeros, basically at these points over here at x is equal to 2, 3, 4, 5, 2 and 5 and negative 3. At this point, and at this point, the polynomial goes through the x-axis, meaning that the polynomial basically goes through the x-axis at this point, goes through the x-axis at this point, and it goes through the x-axis at this point, meaning that the output of your function at these 3 points is going to be equal to 0, meaning that f of negative 3 is going to be equal to 0, f of 2 is going to be equal to 0, and f of 5 is going to be equal to 0. And then of course there are other points also defined. Basically the domain of this function is of course all real numbers. So all real numbers are defined as a part of the domain of this function, or as the domain of this function. And so every other real number would basically any other real number that you input here into this function, you will get some output for that. So now the situation that we have over here, it says that let a1, a2, a3, all the way up to a of n be fixed real numbers, and define a function as this. That means that these numbers are the zeros of this polynomial. And what that means is that the output of this function at a1, a2, a3, all the way up to a of n is going to be equal to 0, of course, right? Now, since this is a polynomial and you want to calculate the limit of this polynomial at, for example, this a1, we said that the limit of, if f of x is a polynomial, and if you want to calculate the limit of f of x as x tends to any a, basically any a basically in the domain of that function, it's going to be equal to f of a, which is in this case f of a1. And here we saw that f of a1 was equal to 0 because a1 was 0 of the polynomial. So that's one thing. And the second question that we have is for sum a, for sum a not equal to a1 or a2 or a2 or a3 all the way up to a of n, compute the limit of f of x as x tends to a. So of course again the limit of the function at when x tends to a is going to be equal to f of a, right? But now there is some part over here that you need to understand about these polynomials, and that is, for example, let's say that in the case of this polynomial, let's draw the graph of this function and see what happens, for example, at x is equal to 1. At x is equal to 1, of course, the output is going to be f of 1. But there is something interesting that happens here, and that is when x is equal to 1, then f of 1 is actually equal to 1 minus 2, because this is your x, right? 1 minus 2 times 1 plus 3 times 1 minus 5, which is equal to basically negative 1 times 4 times negative 4. This is negative 16, and that is positive 16. So f of 1 must be positive 16. Now let's draw the graph of this function and see what happens. If you draw the graph of this function, if y, or basically f of x, if f of x is equal to, what was that? F of x cubed minus 4x squared minus 11x, x cubed minus 4x squared minus 11x minus 40 plus 30 plus 30. As you can see, the function goes through the x-axis at exactly these points 5, positive 2, positive 5, and negative 3. And at x is equal to 1, the output of the function, it is exactly at 16. So at x is equal to 1, of course this is not this, 1 comma 16. So that's basically what happens in the case of a polynomial, and you can see that the polynomial basically from this side goes to negative infinity, goes all the way up to here, up to this point, and then it has a y-intercept over here, goes through the x-axis again at this point, comes down here, up there, and then goes to positive infinity. And of course there are many ways to compute it's actually possible to find out how to graph this function, but in this series of books I actually found I haven't found any chapters on how to graph a polynomial. We will hopefully get to that somewhere, hopefully in the next book probably. So that's basically what happens. So now what that means is that then if basically for some a not equal to the zeros of the polynomial, if you want to compute the limit of f of x as x tends to a, it's of course equal to f of a, which is equal to basically a minus a1 times a minus a2 times a minus a3 all the way up to a minus a of n. So this is actually an interesting and nice question to learn a couple of things about polynomials and how they behave. So there is 3 more questions here to cover. Question number 30 is if f of x is equal to the absolute value of x plus 1 when x is less than 0, it's equal to 0 when x is equal to 0, and it's equal to the absolute value of x minus 1 when x is greater than 0, then for what value s of a, for what values or value for what value or values of a does the limit of f of x when x tends to a, does the limit of f of x when x tends to a exist? Okay, so you need to take a look at the graph of the function, it's always easier to take a look at the graph of the function. I mean, you could understand, of course, the function if you looked at the algebraic representation of the function, but that's usually not the best way. I mean, you could miss a couple of things here. So if I graph this function, for x is less than 0, I have the absolute value of x plus 1, meaning that I would have basically the absolute value of x would be this function over here. and the absolute value of x plus 1 would be the same function moved up 1 unit on the y-axis. So it would be basically this function over here. Now, if you had this function, this is only for x's less than 0. So this part is just simply not there, and this part is also not a part of the function. It's not part of the function either. So that is basically, it's called a part 1. Now it's equal to 0 at this point, at f of x is equal to 0 when x is equal to 0. So this point is a part of the function, and the absolute value of x minus 1 is basically the same absolute value function, but shifted down 1 unit. So you would get basically this function like this, and of course not with that slope. With this slope, this is supposed to be a 45-degree line with respect to this line. So if you had a horizontal line over here, there would be a 45-degree angle between this line and that horizontal line, because it's basically the graph of the function y is equal to x and y is equal to negative x put together in this one package called y is equal to the absolute value of x. So it has to be basically a 45-degree angle between this line and the other line. So what that means is that now this is only defined for x is greater than 0, meaning that basically then this part is just simply not there, and then this part is not there either. And that you get the point over here, and that is your function. So as you can see, for when x tends to 0, of course the limit of f of x does not exist, because your function over here approaching 0, your function is giving you the value around 1, and over here it's giving you negative 1. So at x is equal to 0, the limit does not exist. So you can say that the limit of f of x when x tends to 0 does not exist. And does not exist. Except for that, the limit of f of x when x tends to a does exist for all other a. For all other values of a, except for a is equal to 0. Now, what that means is that for what value or values of a does the limit exist? So a has to be a part of this interval, meaning that a has to belong to the, basically you can go from negative infinity all the way up to 0, and the union of that set with basically 0 all the way up to positive infinity. A has to belong to this interval so that the limit does exist, meaning that 0 has been excluded from these numbers. Another way of saying the same thing is I don't know. There is one more way to say the same thing, of course. Let me see the answer over here. The answer is very simple here and very elegant. What they have said is that the limit of f of x as x tends to 0, as x tends to a, exists for all a not equal to 0. So basically means the same thing, but in a much simpler way, basically. And I wouldn't have probably, I wouldn't have probably understood this from the algebra. I would, but it wouldn't have been so easy. On the graph you can easily see everything, but when it is still in the form of algebra, it's not easy to. It's sometimes, sometimes you get misled. The next question that we have is question number 31. It says if the function f of x satisfies f of x satisfies the limit of f of x minus 2 over x squared minus 1 when x tends to 1 is equal to pi, you need to evaluate the limit of f of x when x tends to 1. Okay, so it says that the limit of f of x basically satisfies this equation, which is the limit of f of x minus 2 over x squared minus 1 when x tends to 1 is equal to pi. That means that the value of this function is actually equal to pi at this point, and it's actually a continuous function at that point, meaning that at that point your function is not broken, otherwise the limit would not exist, right? Meaning that, for example, if you have a function over here, and for example we saw that, for example, in the previous case, for example, we had this situation, for example, and you see that the function over here is broken at this point. The function is broken, so at this point the limit does not exist. But if you had something like this, if you had some situation like this, for example, at this point, let's say that, for example, you have, for example, this situation, this function over here, you can see that you have two parts. For example, let's say for x is less than or equal to 0, the function is this, or x is greater than 0, it's this part. Now you see that at this point the function is not broken, and so the limit does exist at x is equal to 0. Okay, so since f of x satisfies this equation, that means that this function, that means that the value of this function at x is equal to 1 is equal to pi. So then what that means is that you can write f of x minus 2 over x squared minus 1 is equal to at x is equal to 1 is equal to pi. This is just some notation that I remember from college mathematics, I suppose. What this means is that basically the value of this expression at x is equal to 1 is equal to pi. And what that means is that then f of 1 minus 2 over 1 squared minus 1, which is equal to 0, is equal to pi. Which means that f of 1 is equal to positive 2. If you cross multiply, f of 1 minus 2 is equal to 0. So, of course, you're not supposed to divide by 2. So you need to somehow make that at this point. If I set x is equal to 1 here, I would be dividing by 0, which is not very nice. So I need to, and since the limit does exist at this point, I mean that the fact that that this equation, that this expression is equal to pi, that means that this limit does exist and it's equal to pi. So what that means is that I can write this equation as the limit of f of x minus 2 over x squared minus 1 as x tends to 1. This is equal to pi. And now I need to somehow take some, and of course you can rewrite your denominator as the limit of, well, f of x minus 2 over x minus 1 times x plus 1 when x tends to 1 is equal to pi. And that means that f of x minus 2, if you calculate f of x minus 2, one of the, either x minus 1 or x plus 1 has to be one of the, a common factor between f of x minus 2. One of the factors of f of x minus 2 must be either x minus 1 or x plus 1, because that way then basically that common factor would cancel out, and then the limit could exist or would exist. Now how do we solve this problem now? Okay, so it turns out that all of the analysis that we did, although it was not necessary, but well, not really necessary, meaning that well, of course we don't need this step over here, and then basically we have the limit of f of x minus 2 over x squared minus 1 as x tends to 1 is equal to pi. So what that means is that then you can write this as the limit of, f of x minus 2 as x tends to 1 over the limit of x squared minus 1 as x tends to 1 is equal to pi. and then if you cross multiply here, you will get the limit of f of x minus 2 as x tends to 1 is equal to pi times the limit of x squared minus 1 as x tends to 1, and the limit of x squared minus 1 as x tends to 1 is equal to 0. So this whole side of the equation becomes 0. So then you can write the limit of f of x minus 2 as x tends to 1 is equal to 0. Which means that, and I can write this as the limit of f of x as x tends to 1 minus the limit of 2 as x tends to 1 is equal to 0. And I can write this as the limit of f of x when x tends to 1 minus 2 is equal to 0. The limit of constant function is the value of the function. So that then the limit of f of x when x tends to 1 is equal to positive 2. And that is what we were after. Okay, so we have one more question here, which is if f of x is this function and the limit of, for what integers does both the limit of this exist. So your f of x is basically this function over here, mx squared plus n, nx plus m, and nx cubed plus m. This is for x less than 0. This is for x's between 0 and 1, 0 less than or equal to x less than or equal to 1. And this is for x's greater than 1. Okay. Now if you want to know for what values, for what integers m and n, for what integers m and n does both basically the limit of f of x when x tends to 0 and the limit of f of x when x tends to 1 exist. Okay, so you have a second degree polynomial here, you have a first degree polynomial here, and you have a third degree polynomial here. And this is for x's greater than 1, this is for x's greater than or equal to 0, less than or equal to 1. And this is for x's less than 0. Now what we want to know is that for what integers m and n do both of these limits exist, meaning that the limit at x is equal to 0 and x is equal to 1. Meaning that these two polynomials do need to have a point of intersection. If they have a point of intersection at x is equal to 1, at x is equal to 1, then that means that the limit of the that means that the limit of f of x exists at x is equal to 1. If these two polynomials have a point of intersection at x is equal to 0, then that means that basically the limit of f of x exists at x is equal to when x tends to 0. So now let's write these two conditions. If basically if I call this, for example, 1, if I call this 2, and if I call this 3, so basically if 2 and 3 have a point of intersection at x is equal to, this is for at x is equal to 1, then the limit of f of x when x tends to 1 exists. Well, let's see how we can manage that. So what that means is that then basically this polynomial then that means that 2 gives me basically at x is equal to 1, then basically you will have n times 1 plus m. N times 1 plus m is going to be equal to some y, for example, and again basically n times, and then 3 gives us n times 1 cube plus m is going to be equal to the same y. And so what that means is that this is basically n plus m is equal to y, and that means that basically n plus m is equal to y, which, as you can see, I will not be able to solve this equation, I will not be able to solve for n and m because basically they are the same equations, but I can actually take one of these, so I can call it equation number 4. Now we said that if 1 and 2 have a point of intersection at x is equal to 0, now if 1 and 2 have a point of intersection at x is equal to 0, then the limit of f of x when x tends to 0 exists. So then what that means is that this is mx squared plus n. Mx squared plus n, this is supposed to be equal to, this is at x is equal to 0. At x is equal to 0. Mx squared plus n is supposed to be equal to some y. And so if x is equal to 0, that means that n is equal to, some y. And 2 is going to give us nx plus m. So nx plus m is supposed to be equal to some y. And so if x is equal to 0, that means that m is equal to y. Okay, so what that means is that basically based on this you can say that n is equal to m. And I can call this equation number 5. Now, so if so I have n is equal to m, and n plus m is equal to y. So what that means is that then I suppose that's the only thing that we need. If n is equal to m, then n and m could have any values really, but the values have to be exactly equal, which means that number 32 for limit of x raised for the limit of f of x to exist, we need m is equal to n, and the limit of for any integral value of m and n. I see. Okay, so basically we actually got the answer, but we didn't make sense of the answer properly. So you see over here, we said that if these two have a point of intersection at x is equal to 1, then the limit exists, right? And then we solved these equations and we got these two exactly equal equations, exactly similar equations. And so what that means is that the solutions over here for n and m, this means that basically the limit of f of x when x tends to 1 exists for, so what this means is that the limit of this means that basically the limit of f of x when x tends to 1 exists for any integral value of m and n, for any integral value of m and n. And the reason for that is that the reason why these have to be integers in the first place is that I don't really know why they have to be integers, because normally they could be any number really, any real number, unless I don't really know why they have to be integers. But when you have a system of equations in which the two equations are exactly the same, so what this means is that n plus m is equal to n plus m, which means that 0 is equal to 0. And that means that Okay, we'll have to make sense of this using some sort of example. But what this means is that basically the limit of f of x when x tends to 1, this exists for any integral value of m and n. And keep in mind that we got basically this situation over here, which was basically m plus n is equal to y and m plus n is equal to y. This was the system of equations that we got. So this is for this part. Now we will deal with this sometime later using some proper example. And I suppose we can actually use this exact same this particular situation, because based on this situation we will be able to understand the concept much better. Now this is this part. Let's move on to the next part. We said that now, of course, then the limit of f of x when x tends to 0 exists if n is equal to m. And since there is no condition here, so we can just simply say that if n is equal to m, then both of the limits exist. But now about this part, you see the situation is a little bit, we have basically, we were basically talking about these two lines, nx plus m and nxq plus m, these two lines. And we said that these two lines, if they have a point of intersection at x is equal to 1, then basically the limit does exist. Okay, now what we did was that we set x is equal to 1 in both of these equations, and we got basically two equations in terms of n and m, which were practically these two equations, which were the exact same equations. So then what that means is that n plus m is equal to n plus m. Then you can cancel out n's and m's from both sides of this equation, and you will get 0 is equal to 0. That means that there is no condition on n and m, something like that. Oh. Well, since n and m basically simply cancel out from this system of equations, that just simply means that it doesn't matter what their values are. So that's basically, I suppose, why we can say that the limit of f of x when x tends to 1 exists for any integral value of m and n. But now there is one more question here that I don't understand, and that is why these values have to be integers at all. That part I don't understand, but other than that, all the other parts are easy to understand. So if you know why these values have to be integers, you can please let me know. If you happen to know the reason, you can please let me know. Okay, so that is that. Now the next part that we have here is about derivatives. is about derivatives. We have some definitions and so on and so forth, some examples, and so we will get to that in the next video. See you in the next video.